Hey, welcome back, everyone. Today we're going to talk about matter, energy, and forces, and then we're going to discuss some of the earliest discoveries and experiments that led to the postulates of the atom. And we'll talk about elements as well. But today's lesson represents approximately the first half of chapter 2. So you might read a little bit ahead. Always reading ahead will help with these lessons. Or you can read after the lesson, whichever works better for you. Here's a little breakdown of the schedule of the topics I'm going to cover. Let's start off with thinking about the fact that everything that makes up the universe is made of either something we call matter or something we call energy, and it exists in a framework called space-time. Space-time is just some time that exists at a place represented by x, y, and z coordinates. Now, the universe is really complex, and I have this really cool wall chart that I really like to look at when I'm trying to think about different topics I want to talk about in chemistry, and we can see here that matter comprises of a lot of different things. It comprises of rocks, meteorites, minerals, the elements. It can consist of fundamental particles. And then we have these things called forces. Forces are the things that act on particles, like photons, like light. That's a type of force. Or actually, that's the particle. The interaction is the photon. But the force, these four common forces. I'll talk about these in a little bit. But we can see that the universe is made up of both matter and energy. And matter and energy, those are things that are actually interchangeable in some sense. But that's more of a nuclear chemistry topic. One thing I like to point out here is that is the different composition of the body and the sun and the earth. So the sun was formed about 4.5 billion years ago, and same thing with our planet and our solar system, all formed around the same time. Our sun is made up of mostly hydrogen and helium, and then a small composition of other elements, whereas our earth is made up of mostly iron, oxygen, and silicon. And then our body is made up of mostly oxygen, carbon, and hydrogen. So matter is very variable depending on where we're talking about in our universe. And within our own planet, it varies very much so. So all of these different minerals here are made up of different compositions of different elements. And you can learn a lot more about this when you go on to study like geoscience, for example. So if we look at the composition of the universe as a whole, it's made mostly of free hydrogen and helium, but then it's also made up of these other things that we don't typically talk about in chemistry. It's these forms of matter that don't interact with light, that's known as dark matter, and then a form of energy that we're not very familiar with, it's called dark energy. So 95% of the matter and energy in our universe is of this kind of mysterious origin. We don't really know too much about it. But the remaining 5% is of this ordinary matter, which is baryonic, meaning it has protons and neutrons that make it up. Things that we can see, feel, and measure directly. Things like stars and planets, galaxies, humans. All those things are made up of atoms. And as a whole, most of the universe is hydrogen, but a lot of the other stuff that we interact with on a daily basis is other materials, other elements. And then there's other energy that's associated with that matter as well. So we'll talk about energy a lot today too. So I like to go through and discuss matter, energy, and forces in like a flowchart that we can talk about. And this flowchart might be helpful for you as you go through the course. You might come back to it. But I made these flowcharts to help us see the differences between these terms that sometimes get used interchangeably when they shouldn't be. So let's start by discussing what matter is. Matter, as I described in lesson 1, is anything that has mass and takes up space. And matter makes up the substances that are in the universe. We can classify matter in terms of how it's separated. And either it's separated by physical or by chemical means. So if we start here at the top, if matter can be physically separated, we call it a mixture. And types of physical separation are things like filtration. So if I have a filter that has coffee grounds in it, and I have water that I've poured on top, the water will extract some of the water-soluble materials into the water, and then we'll be left with the coffee grounds on the top, and then the water on the bottom. And so that would be a mixture, right? So we'd have a coffee ground mixture. We could also further separate the things inside the water, right? But there's other types of separation techniques like distillation. So I can separate two different liquids that are miscible by their boiling point. So I could take a more volatile liquid that evaporates more easily and apply heat to it, and then collect that the lower boiling point liquid in a separate area. So that's distillation. A related technique is evaporation. So I can just let a mixture that contains a solid particulate evaporate from that, and then you're left with the solid, and then the liquid goes off into the atmosphere. We can decant a mixture. That means just like pouring it slowly and leaving behind any solid material. If we have a ferromagnetic material like iron, we can take a magnet, we can separate it out. We can use a centrifuge to spin down mineral or material that will separate from other material. So that's another way we can separate out materials. There's a lot of other techniques: chromatography, sieving, sedimentation, sublimation, extraction, precipitation, recrystallization. These are all terms you'll learn about as you study chemistry. They're all different techniques that scientists have used to try to separate out all the different things that make up a mixture. And a lot of times, most of the things that we'll study are mixtures. So let's start with that grouping there. So say, for example, we are able to separate stuff out. We have this thing called a mixture. Well, if we look at that mixture, we can break it down a little bit further. We can ask the question, is that composition uniform? Meaning, when I look at it, is it visually distinguishable from one another? Like, if I have a chocolate chip cookie, I can distinguish the chocolate chips from the rest of the cookie, right? Versus a cookie that had nothing like on it, right? So something that is uniform throughout, that would be something that's homogeneous. So a liquid that, like water, like tap water, has other minerals that are dissolved in it, but visually it looks as if it can't be distinguished. It's equally mixed throughout. And there are a variety of different homogeneous mixtures. There are gaseous mixtures. So when we look at air, we can't really see air, but if we had a sample of air we're trying to analyze, it would be approximately 78% nitrogen, 21% oxygen, 1% argon. There would be 440 parts per million approximately of carbon dioxide. And then there'd be like less than 1% that's a trace gas, such as water vapor or ozone. So there are a lot of different things that make up the air that we breathe. It's a mixture. It's not a pure substance. Then we could also look at a metallic mixture, and these are often called alloys. So if I have a solid that's dissolved in another solid, like a 14 karat gold ring, depending on how it's made, if it's white gold or it's regular gold, it could have a varying amount of silver and gold or nickel in it. And then we could have a specific type of alloy called an amalgam. That's when you have mercury that's dissolved in another metal. So that's an interesting type of alloy. And then you have these liquid homogeneous mixtures, which are typically called solutions. And a solution is a substance where you have a small amount, a solute, dissolved in a larger amount, the solvent. And a couple of common examples of that are salt water, sugar water, and vinegar. Vinegar is acetic acid and water. Also coffee. Coffee is a mixture of various alkaloids that are found in the coffee plant, one of which is caffeine that we're interested in. But coffee is definitely a mixture. Now, a lot of the things that we're going to study are heterogeneous mixtures, meaning we can kind of visually distinguish between the components or phases that are in them. Some examples are wood and granite and minerals. So a lot of these, a lot of these rocks here are you can visually distinguish like different parts of these rocks from each other, right? So these are heterogeneous mixtures of minerals, okay? And they come in a variety of different forms and shapes and sizes. And then we have other types of things we can talk about. So we can talk about where we have mixed phase solutions. So if I have two liquids that don't mix, and you can see two phases of them, like oil and water. So if I have oil and water, the oil will be on top because it's less dense, and then I have water that's more dense on the bottom. I could have a suspension. That's where I have a solid particle that doesn't quite dissolve in the liquid, but it still remains evenly distributed. So blood, like red blood cells, when they're in your blood, they're suspended in it, right? They dissolve. They don't dissolve well, but they're like evenly distributed throughout. Paint's another example of a suspension. You can kind of see that it looks. It's not clear, right? You can't really see through paint because there's all these particles in there that are just kind of dispersing the light that's in them. And then there's a different type of suspension called a colloid, where you have very fine particles that are actually finely dispersed in another. So here we have like a solid in a liquid or a liquid in a gas. Milk is an example of a colloidal substance, colloidal mixture. Where you have the little micelles, like fat micelles, dispersed in the water that makes up the milk. Fog, that's where you have a liquid dispersed in the air. So we have a lot of different nuanced types of mixtures, and these can be very fun to kind of study. And then what other types of matter are there? Well, if we aren't able to use one of these physical separation techniques, then we, as chemists, are going to call this a pure substance. And a pure substance could be broken down chemically, so not a physical separation, but a chemical separation. So if we have an advanced technique like a chemical reaction, electrolysis setup, a type of reaction like that uses acid-base chemistry or oxidation reduction chemistry, we might be able to discern whether we have a compound or whether we have an element. A compound is where we have two or more different elements that are bonded together. So water is a simplest example of a compound. We have 2 parts hydrogen and 1 part oxygen. And then we have something like table salt, which is 1 part sodium to 1 part chloride. And then we have sucrose, which is 12 parts carbon, 22 parts hydrogen, and 11 parts oxygen. So here, each of these compounds is made up of two or more different elements, and they're bonded together in some way, either by a covalent bond or an ionic bond. And then if we are not able to chemically decompose this pure substance, then we must have something called an element. An element, in its simplest definition, is where we have one type of an atom. And this can be a little different than how we typically think of it. Like we have the periodic table of the elements, and when we look at the periodic table of the elements, we'll have just one symbol listed. But the correct definition we should be using is where we have a pure substance that can't be broken down any further. So gold exists as Au, is just one gold atom bound. There's a bunch of gold atoms, and they're metallically bound together, but there's a bunch of them. Then we have aluminum, which is Al. And then we have oxygen-based elements. We have oxygen, which is O2. But then we have an allotrope of oxygen, which is O3. So oxygen can exist as varying different types, right? So we have O2 or O3. And then we have nitrogen, which is N2. And then there's a variety of different elements that exist as their diatomic form or as a higher order form. The ones that I want you to know are these ones. So like hydrogen is always going to be H2. It doesn't want to be by itself, and we'll learn about this later on in this class when we start talking about electron configurations, about why hydrogen exists as H2. And then also like the other ones are N2, so the one I have here, nitrogen. Oxygen is typically O2. Ozone is a less common form of it. Then we're going to have our halogens. So we have fluorine. Fluorine exists as the element F2. Chlorine, bromine, and iodine. Right. So these are, interesting that these are the only diatomic elements that we need to know. So there's 1, 2, 3, 4, 5, 6, 7 of them for you to kind of memorize. These ones here are gases at room temperature. Bromine here is a liquid. And iodine is typically a solid at room temperature. And then there's two related related elements. So typically when we have phosphorus exists as a tetragonal form. It's P4. And then we also have sulfur. Sulfur typically exists as this octagon shape. It's eight elements in a ring. So we'll have P4 and S8. Both of these are solids. So elements, compounds, and mixtures. Make sure you know the difference between those. Now, how can we classify energy? Energy is something that's different than matter. It's what enables matter to move and change. We have 4 major types of energy that I've broken this flowchart into. We have electromagnetic energy. Electromagnetic energy is anything that has electrical and magnetic properties, such as light. So light is a form of electromagnetic radiation. There's the sunlight that we see, but there's also other types of light that we can't see, but we know exists, like radio waves, microwaves, X-rays, infrared radiation, UV radiation. Light is just that small component that we can see with our eyes. Radiant energy is all the other types of light energy. All right, then we have energy that moves. That's kinetic energy. And then we have energy that has the potential to move, which is potential energy. And then we have energy that's associated with the change in the composition of the atom. That's the nuclear energy. So let's start with kinetic energy, energy that allows matter to move. We have mechanical energy. So anytime we have an engine or a turbine that can take motion and or convert into motion, that's known as mechanical energy. We can also have thermal energy, like steam. And then there's electrical energy and sound energy. So electrical energy, we can think about all of the all of the appliances that we have hooked up in the house or hooked up to the power lines. There's 120 volt line coming to each of our appliances, or maybe 240 volts, and that's a type of energy that allows for us to turn on and power things. And then even sound energy is something that we can be appreciative of. If we're at a concert and we're near a speaker, we can feel the vibrations. And then there's 2 or 3 main types of potential energy that are worth noting. And chemistry, we're going to be spending a lot of time thinking about chemical energy. And chemical energy, that's found in the bonds between atoms in a molecule or a compound. And when we break those bonds, we release energy. And that's why food and gasoline are both able to power either our stomachs or our cars, is because they have molecules in them that have energy in their bonds that we break, and then they were able to extract that energy or utilize that energy in some way to power our body or power our car. And another common type of potential energy is gravitational. So we can make use of the gravitational energy, like in the sense of dams. We can take the water that's falling and convert it into energy. If we have a rubber band that has a type of potential elastic energy in it. And then what we won't talk about in this class, but is really fascinating, is fission and fusion energy. So fission energy is what powers like nuclear power plants. It comes about from the spontaneous fission of uranium-235. And then you have fusion energy, which is what powers stars, where you have hydrogen coming together to form helium, and in the process it loses a little bit of matter, and then it converts that matter into energy. And that when that occurs on an atom by atom basis, it adds up to a lot of energy based off of Einstein's energy mass equivalence equation, E equals mc squared. So here we have a lot of different types of energy, and they can transform from one form to another. And we can't really observe energy directly. We can only observe it when it changes. But what we do know is that the total energy in a closed system remains constant. And we'll talk about this when we get to thermodynamics later on in the class. Now, this is one component of the class. It's a little outside the scope. It's where we start to classify what forces are. And I think it's interesting to talk about. So forces are the interactions that dictate how energy and matter behave. So we have 4 main fundamental forces. Gravitational force, which is the force of attraction between all masses. So anything that has a mass will be attracted to another thing that has a mass. Now, the structure of the universe is largely dictated by gravitational forces, the orbits of our planets, the gravity that we observe on Earth. And interestingly, it is the weakest force, but it has an infinite range, and it's always attractive, and it acts on all particles. So that's why it is kind of what gives rise to the structure of the universe. Because some of these other forces we'll talk about have very differing effects. So the electromagnetic force This is the force between anything that is charged, any charged particles. And it's carried by a small packet of light called a photon, which we'll talk about a little bit more at a later date. And so it can be both attractive or repulsive. So anything that has the same charge will be there will be a repulsive effect. Anything that has differing charges will be attracted to each other. And it's much stronger than gravity. It also has an infinite range, but it only acts on quarks and leptons. So a quark is something that makes up a proton and a neutron, and a lepton is a type of subatomic particle like an electron. So let's say it acts on all atoms and acts on all electrons. Okay. And then we have two types of nuclear force. We have a weak nuclear force and a strong nuclear force. The weak nuclear force is what gives rise to radioactive decay, and it's carried by these particles called W and Z particles. Now, during a beta decay process, these particles result in the changing of an atom to either to convert a proton, or sorry, to convert a neutron into a proton. And so neutrons and protons can actually be converted through this nuclear decay process. It is a weaker force than electromagnetism. It acts on a very short range. It acts on quarks, so it acts on protons and neutrons. It acts on electrons, which are charged leptons, and it acts on the W particle. So that's a weak nuclear force. And then we have the strong nuclear force, which is any force that binds protons and neutrons together. And we'll talk about the proton in a little bit, but the proton is a positively charged particle, and they all exist in this region of the atom called the nucleus. And the proton is very close to other protons. And based off electromagnetism, you would think that the protons would repel each other. But this strong nuclear force overcomes that, and it holds the nucleus together. It's carried by the gluon, so the strong nuclear force can be remembered as the glue that holds the nucleus together. It's the strongest force by all, but it only acts at a very, very short range, on the order of 10 to the negative 15 meters, which is the femtometer range. It only acts on quarks and the gluon. So it doesn't act on leptons. So it doesn't act on electrons. Okay. So we have gravity, electromagnetism, weak and strong nuclear force. And then we have this other particle called the Higgs particle. And it is a fundamental field. So it gives rise to a fundamental field that gives mass to all particles. So what gives rise to some matter having mass? Well, it's the Higgs particle. Without it, nothing would have mass. Neil deGrasse Tyson describes the Higgs particle as like a celebrity, like Beyonce. When Beyonce walks into a club, Beyonce has a large Higgs field because everyone wants to is attracted towards that celebrity, right? So everyone wants to be near Beyonce. But if it was just me walking into the club, I'd be like able to walk to the bar with no problem, okay? Because I don't have a huge Higgs field around me, okay? So it's just some particle that when any type of matter gets near it, it gives rise to gives it mass to the other particles. It's an interesting thing. All right, so let's talk a little bit more about the elements here. When you look at a multivitamin or a multi-mineral tablet, you'll see that it lists all these different elements and their percent daily value, and it gives you a mass here. These are milligrams or micrograms, mcg, and each of these elements is actually in the form of a compound rather than it by itself. So zinc is zinc oxide, iodine is potassium iodide. So they don't just exist here in the pure element, but we're already familiar with a whole bunch of them. And the elements are necessary for life as we know it. I mean, there could be synthetic life without elements, but I don't believe that would be able to be possible. There are 94 naturally occurring elements on Earth, hydrogen, all the way through plutonium. And on our course page, you'll find a really nice periodic table that we can make use of. I encourage you to print this out. It's just right down here at the course resources. And so this periodic table is a free one that I put together. Has the names of all the elements and their symbols here. Okay. So 94 of these elements are naturally occurring. That's hydrogen through plutonium. So elements 1, hydrogen, through plutonium, which is 94 down here. And then you'll see these asterisks. So these elements 57 through 70, they fit in right here on the periodic table. And then elements 89 through 102 fit in here between radium and lawrencium. So the periodic table, we'll talk about how it was organized and all that in a little bit. But now 80 of these elements, from hydrogen to lead, have at least one stable isotope that doesn't undergo radioactive decay, except for technetium and promethium, which are exceptions. So we have 80 stable elements. Okay. Now there are synthetic elements as well that are produced through artificially through nuclear reactions. So elements greater than uranium, neptunium, all the way through oganesson can be created synthetically with the help of a nuclear reactor. As of now, scientists have discovered 118 elements, the last of which is oganesson. The most recently discovered was element 117, which is Tennessean. So actually we discovered 118 before 117. Now these elements here were only discovered at the atom level, right? So we've only discovered a few atoms of some of these elements, which is not very many, but it's enough to say that they can exist, even if they have a short half-life. We've known a variety of these elements since ancient times, right? But the discovery of most of these elements occurred in a quick period of time in the 1700s and 1800s. And scientists have not given up on this. So I think in like a year or two, we'll have element 119 or 120. And then in that sense, we'll have to add another row to the periodic table. We'll have to add period 8. There may be a fundamental limit to how many elements there can be, but that would end at probably 137, because after element 137, there's these competing forces, right? So we have this nuclear force which is holding together the nucleus, and then we have the electron that's going around the nucleus. When you get to really, really heavy atoms, the speed of that inner electron increases and increases, and at some point, the speed necessary for it to stay together would be faster than the speed of light. So essentially, this atom would become unstable and break apart. All right. So what can we know about all these elements? Well, we can apply atomic theory to understand the differences in these elements and the similarities. And the chemical properties for these elements are largely going to depend upon the atomic number. So how many protons that element has. And that's the number of protons that element has determines the charge on the nucleus, because protons have a positive charge in terms of the unit charge E. So so let's say here we have element 6, which is carbon. The charge on the nucleus is going to be plus 6E, plus 6 elementary charges. And we arrange the elements based on the number of protons that they contain in the nucleus. It used to be that elements were arranged based off their mass, but there's a few discrepancies. So if we look, for example, at element 27 and 28, we'll see that the average atomic mass, which is this bigger number here, the smaller number is the number of protons. The average atomic mass actually decreases here. And this is one of those exceptions here. But cobalt has 27 protons, so it's listed before nickel. And there are a couple of different situations. Like here, we can see tellurium and iodine. That's another notable exception. Okay, so atomic symbols, they are given by a capital letter to begin with. So hydrogen has a capital H. And then the next element is helium, but helium has a capital H followed by a lowercase e. So the first letter is always capitalized, the second letter is always lowercase. And then we have some examples like lithium, and there's a whole bunch that we can know. So we don't need to memorize all 118, but we should know a couple, right? So like capital C, that's carbon, but Cu, that's copper, whereas Co is cobalt. There are, a variety of other ones we need to know: oxygen, nitrogen, and then remember those are the diatomics. So they actually, those are the atomic symbols, but the element is O2 or N2. And then we have a bunch of other ones. Like here's a fun one: Xe, xenon, or Kr, krypton. And there's 50 elements, I think, that are worth noting. Here are some flashcards I have. Let's see. So I have gold, argon, hydrogen, lithium, bismuth, boron. So roughly the first couple periods of the periodic table, plus any common groups like the alkali metals and the noble gases. But yeah, I mean, there's a couple reasons why you should know these, right? Every time that you are carrying out a problem that involves balancing a reaction or naming something, if you have to constantly refer back to and figure out, oh yeah, like Al is aluminum or Hg is mercury, you risk making a mistake or you just kind of slow yourself down. And this is part of the language component of this class. So knowing the elements and how to communicate them to other people is going to make you a better scientist. All right, so let's get into some of the scientific experiments that led to the discovery of the atom. Here we have Antoine Lavoisier and his wife, the parents of modern chemistry from lesson 1. And they were jointly responsible for the law of conservation of mass. And in a chemical reaction, when we carry it out, the total mass of the reactants is equal to the total mass of the products that are formed. So let's look at one of the reactions that they carried out. They were studying mercuric oxide, which has the formula of HgO. So This is mercury 2 oxide. And this is a solid compound. And when you apply heat to it, it breaks down into mercury, which is a liquid, and it breaks down into oxygen gas. Now, at the time, it wasn't sure whether oxygen was monoatomic or diatomic. We now know that it's diatomic, and that's a gas, right? And then this reaction isn't balanced properly because we have one mercury on the left and one oxygen on the left, but we have two oxygens on the right. And we'll talk more about balancing in a little bit, but here we should balance it. And here's the chemical reaction that they studied. And here I have three states of matter. I have solid, liquid, and gas. I have this triangle symbol, meaning heat has been added. And I have these symbols that represent the elements. Hg for mercury and oxygen, so O for oxygen. I have subscripts here representing, there's two oxygens in this molecule. This is a compound between mercury and oxygen. And we'll learn all about these differences here. But if we carry out this reaction, the total mass of mercury 2 oxide at the beginning needs to be equal to the mass of mercury and oxygen afterwards. And these studies of mercury and oxygen were carried out to debunk this idea of phlogiston, which is this which was this idea that when you heated a substance, it either released this substance or it absorbed this substance. But what people were misunderstanding was oxygen. So Lavoisier, the Lavoisiers were responsible for helping people understand that oxygen is a very important substance. And so total mass before and after should be the same. So say, for example, we started with 5 grams. We should have the sum of these two needs to be 5 grams at the end. Okay, so the second discovery was by Louis Proust. He realized that anytime that you have a pure substance, a pure compound, the relative amounts of each of the elements in that compound is always going to be the same, regardless of the origin or regardless of the preparation. So let's look at a different chemical reaction. Let's say we look at the electrolysis of water. So if I take pure liquid water, this is a pure substance. I can break it up into its elements. I can break it up into hydrogen and oxygen. And hydrogen and oxygen are both diatomic. So it breaks up into hydrogen gas and oxygen gas. Here I need to balance this reaction. It's not balanced, so let me go ahead and do that. I'll put 2 here, and then I'll put a 2 here. And we'll learn about how to do this in a little bit. But here I have, for every 2 parts of water, I get 2 parts of H2 and 1 part of O2. And that's going to be the same whether I got the water on Mars or whether I got the water here on Earth. I could have got it in the Alps, or I could have got it in a stream from the Boise River. This water is always going to be 2 parts water, or 2 parts H2, and 1 part O. So water is always, we can just look at the chemical formula here, 2 parts hydrogen to 1 part oxygen. if we go to make this measurement here, say for example, we start with 9 grams of water. Okay, we have 9 grams. When I go to carry out the experiment, we're going to find that it's going to be 1 gram of hydrogen and 8 grams of oxygen. And the reason why it's not, why the masses are different is because the mass of hydrogen is less than the mass of oxygen, okay? But regardless, water is always 2 parts hydrogen to 1 part oxygen. For a long time, people thought that water was HO, and that was because they misunderstood the fact that hydrogen and oxygen are diatomic. So I think our textbook talks a little bit about that. All right, and then the third law that was really important was discovered by John Dalton. And he realized that when you have a given element and it combines with another element to form 2 different compounds. So sometimes this will happen, right? Depending on how you do the reaction. But the ratio of the 2 elements for a fixed mass of the first will always be consisting of small whole numbers. All right. So what does that mean? So let's take an example where I have a molecule that's made of carbon and oxygen. So okay. And so we have molecule 1 and we have molecule 2. So depending upon how we combine that carbon and oxygen, we can get a couple different compounds. We could get carbon monoxide, or we could get carbon dioxide. All right, so let's look at how many grams there would be in each of these. All right, so say for example we have 1 gram of the carbon in the carbon monoxide. Well, oxygen's a little bit heavier, so when you do the math, you come out to find that the oxygen here should be 1.33 grams. Now, what would be the amount of oxygen here in the second one? Well, for a fixed mass of the first, so we're going to keep the grams of carbon the same, the amount of oxygen needs to be double the amount of oxygen in the first, right? So it needs to be a ratio of the 2 compounds in small whole numbers. So this times 2 comes out to be 2.66 grams of oxygen, right? So this is an interesting thing. We never notice that we form something like a 1.5 times amount. We never get carbon with 1.5 parts oxygen. That's not feasible. And so that's just a notable law of chemistry. It's the law of multiple proportions. Now, John Dalton went on to try to understand how these laws could make sense. What was giving rise to the law of conservation of mass, the law of constant composition, the law of multiple proportions? Well, he might have been looking at the work of Democritus and Leucippus in 5th century Athens, 5th century BC Athens, who were the first atomists. They believed that, all matter fundamentally, when we break it down to the smallest level, is made up of the atom. So if we had a very fine knife and we were able to keep cutting that material in half and half and half and half, eventually we get to a point where we can't cut it down any further, because then we lose the properties of that material. So the matter is made up of something called an atom. Atom stands for something that's not divisible any further, that can't be cut further. Atomos, uncuttable. So Dalton postulated, meaning he hypothesized without any evidence, just to kind of make sense of these laws, this is his theory, that all matter is made up of atoms that are indivisible. His second postulate was that all atoms of a given element are identical in mass and properties. So all of the carbon atoms in carbon monoxide are identical. They all have the same mass of each other, and they all have the same properties of each other. The third postulate that he had was that atoms of different elements differ in mass and in their properties. So we have oxygen now. So oxygen has a different mass. So that's why it's heavier. It has different properties too, which is why oxygen can burn. So compounds are formed by a combination of two or more different kinds of atoms. So here I have carbon monoxide or carbon dioxide, two or more. So CO and CO2. So they're different kinds and different combinations. And then the last thing he believed is that chemical reactions are a rearrangement of atoms, where we have no atoms that are created or destroyed or transmuted. They just rearrange. So if we look at the water molecules here, we have H2O. That would be where we have an oxygen atom surrounded by two hydrogens. Well, during the electrolysis, we break those bonds and form new bonds between the hydrogen atoms, and then we form an oxygen molecule in the process as well. So here's that last postulate. Now, some of these ideas are not entirely correct. These were just his initial postulates, and they make sense when you're trying to understand some of these laws, but there are a couple nuances that I want to kind of point out here. So it is not true that atoms are indivisible. In fact, atoms can be further subdivided. And they can be divided into protons and neutrons and electrons. Here's another thing. Can protons and neutrons be divided further? Yeah, they can. And they can be broken up into quarks. Electrons cannot be. Electrons are, as far as we know, a fundamental particle. What about this one here? All atoms of a given element are identical in mass and properties. Well, maybe you're familiar with isotopes. If you're not, we'll talk about it in just a moment. But isotopes are not identical in mass, nor in property. Some of them are similar, but many are not. And so the existence of isotopes, meaning an element that has the same number of protons, but different number of neutrons. Atoms of different elements, different mass and properties. I mean, that makes sense, yeah. And then 4 compounds are formed by a combination of 2. I mean, 4 is pretty much correct. There are a small number of compounds that are what we call not indefinite proportions, or like they might have like they might have a weird non-stoichiometric amount, but we can ignore that. And then number 5, this is correct as well. We might want to mention, though, in nuclear reactions, we can actually create atoms. but this is correct in terms of chemical reactions, right? Okay. So, so let's keep going. Atomic masses are relative. So what does this mean here? Well, if we look at this figure from Dalton's work here, he broke down the elements here and he created his own symbols. So this is before the symbol for H was existing. So H, this would be hydrogen here. And then I forget what some of these symbols refer to. Like 8 here, this is referring to oxygen, O. And then I think the one before it should be nitrogen. And then he looked at these like binary compounds. So this one here would be hydrogen and oxygen. So the number 21 here, he was calling an element. He was calling this a binary element, which is water, which is not what we call an element now. We call it a compound, and it's H2O, not HO. He was looking at ammonia and all these different things. So this is just kind of like for history purposes. But atomic masses are relative to one another. So say, for example, we're trying to rank these elements together, right? So I want to compare them. What we typically do nowadays is we standardize the carbon-12 isotope as the standard. So what we'll do is we'll say if we have a 1/12 of a sample, of a 12-gram sample, of carbon-12, that will be equal to 1 atomic mass unit. 1 atomic mass unit is equal to 1 U or 1 Dalton. So these are all different ways of saying the same thing. Okay, so this is how we can relatively compare differing atoms, because before we had an understanding of exactly like the mole and how much an atom weighed, this would be how we can compare them all. So when we look at this chart, what ends up happening is that we'll have hydrogen, and hydrogen will end up being 1.008 AMUs on this scale. We'll find that oxygen is equal to 16.00 AMUs on this scale. Carbon will be equal to 12.00. If we're talking about carbon 12, it'll be equal to 12.00 AMUs on this scale. And something like iron, on average, would be 55.845 AMUs. And so atomic masses, they're relative to one another. All right, so let's do a couple practice problems before we end this lesson. In the next one, I'm going to talk more about the structure of the atom. All right, so I'd pause the video and try to do some of these problems on your own. These ones are pretty good. Now, the first practice problem here is, how could you separate table salt from sand? All right, so let's think about what this would require. So if we have a mixture of table salt and sand together, I gave it away, it's a mixture, right? We can physically separate the two. So we need to think of a physical separation technique in which to separate the two. The first experiment you're going to do in our lab is actually this one. It's where you're going to essentially dissolve the salt in water. So it would be very time consuming and probably not very accurate to try to pull apart all the salt particles from the sand particles, because some of the sand particles are going to look like salt particles because sand has a variety of different colors to it. So maybe we want to dissolve the mixture of salt and sand in a small quantity of water. the salt is going to dissolve, but the sand will not. So then what you can do is you can then take a filter paper, and you can filter out the sand from the salt water. So the salt is now part of the water. After that, we need to separate the salt from the water because we want to actually have them as pure substances. We can dry the sand because it'll still be kind of wet. Maybe using a hot plate or in the sun. And we can evaporate off the water to physically separate the salt from the water. All right, so we're making use of a couple physical separation techniques in that one. All right, in this next problem, 1.28 gram sample of copper is heated with sulfur to produce 1.60 grams of a copper sulfide compound. What's the mass percentage of the copper and the sulfur in the compound? So here we don't know what the we might not know the chemical formula here. So what I'm going to do though is I'm going to take these elements and I'm going to convert them into their symbols. So copper is Cu and sulfur is a capital S. So these are the ones we need to start remembering. And it's going to form a copper sulfide compound. Okay, so I have copper plus sulfur, and it's going to form some copper sulfide compound. And we don't know how many of each of the coppers and sulfurs there are. And so there's going to be this many coppers, this many sulfurs, and so on. All right, so what's the mass percentages here? So we have 1.28 grams. And then we have an unknown quantity of sulfur. And then we have a total quantity of 1.60 grams of the mixture. So what is this unknown amount? Well, we can just take the difference between the two. 1.6 minus 1.28 by the law of conservation of mass will get us that value. So that should be 0.32 grams of sulfur. And then what's the mass percentage of copper and sulfur in this compound? Well, it's the mass percentage is just going to be 1.28 divided by 1.60. That's how much times 100 is how much copper there is. And 0.32 divided by 1.60 times 100 is how much sulfur there is. So it's just the amount of that element divided by the mass, the mass of that element divided by the mass of the total sample. So 80% and 20% will be the other one. How could we figure out what the formula here is? Well, we might want to look at the atomic mass units for copper and sulfur. So on the periodic table, copper has an atomic mass unit, like an atomic weight of 63.55, and sulfur is 32.06. So let's see what we get when you multiply this out. Okay, 50.84 grams of or 60. Okay, hold on a second. 22. Oh, we don't want to do it that way. Actually, I think we're just going to leave it this problem like this for now. Okay, so that's how you find mass percentage. And then for problem 3, a sulfur forms 2 different oxides. So an oxide is when you have a compound combined with oxygen. This is going to be looking at something like this law of multiple proportions here. Okay, so we'll have to make a table like this. One of these oxides is going to have 1.87 grams of sulfur combined with 1.87 grams of oxygen. And in the other, we have 3.94 grams of sulfur combined with 5.91 grams of oxygen. And we want to illustrate the law of multiple proportions. Well, what we want to make sure we do is that when a given element combines with another element to form 2 compounds, we want to have a fixed mass of the first and compare the ratio of the 2 compounds. So we can either fix the sulfur and then look at how the oxygen changes, or do it the other way. Since we're looking at oxides, I think it would make most sense to fix the number of grams of sulfur. So let's look at the sulfur plus oxygen compounds. So we don't know what they are. So we'll just call them molecule 1 and molecule 2. And then in one of them, we're going to have our sulfur in grams, and then we'll look at how much oxygen there is. Okay, so molecule 1, let's say it has 1.87 grams. And then this one would be 1.87 grams of oxygen. I'm just going to leave out the grams here. And it's written here up in the label here. And then molecule 2, well, 3.94 and 5.91. Well, we can't compare these until we have a fixed number. So if we divide this by 1.87, hold on a second. Okay, I paused it for a second so I could think this through. So what we want to do is we want to create a ratio so that this equals 1.87. Okay. So what do we need to divide this by? Well, this divided by 1.87 gives us 2.1069. And then if I divide this number here by that same number, 2.1069, I won't have changed anything. So 5.91 divided by that gives me 2.805. Okay. So here I have a fixed amount of sulfur, and the oxygen changes. Okay, so it goes up from 1.87 to 2.805. All right, so what is the difference in these values? What is 2.805 divided by 1.87? It is 1.5 times as much. So this second molecule of sulfur has 1.5 times as much oxygen. Now, if the simplest molecule we were thinking of was SO, then we would get a compound that would be SO and SO 1.5. But we know that can't be the case. So we have to think about something that's a little bit more complex than that. So what about if we have Okay, so if instead of SO as the starting molecule, the starting molecule is sulfur dioxide, SO2. If we were to have 1.5 times as much oxygen, then we'd have SO3, sulfur trioxide, as our second molecule. So it's hard to know what the first molecule is, but if you know that you have two different compounds that combine together, or two different elements that combine together to give you two different molecules, you might be able to deduce what that first molecule is. And this was what like early chemistry was all about, is like trying to figure out what the composition of some of these simple molecules was. All right, so that's that problem there. And so these are possible based off of the math. Okay. Now, this is an interesting problem. So suppose we decided to establish an atomic mass scale by setting the atomic mass of carbon-12 to exactly 1. What would be the atomic masses of naturally occurring hydrogen and oxygen on this scale? Well, if we look at okay, so normally in this problem, we would think that carbon-12 would be equal to 12.00 grams. So carbon-12 is normally equal to 12.000 grams. But in this scale, we're going to set it equal to 1.000 grams instead. All right, so then if we want to figure out what the new atomic mass of hydrogen or the new atomic mass of oxygen would be, we would just have to set up a ratio. So let's look at for hydrogen, for example. So hydrogen is normally 1.008. If we look at the periodic table here, 1.008. And then oxygen is normally 15.999. And if we divide these two together, we'll get what the new atomic mass of hydrogen would be. Wait, what did I do wrong? All right, so we can see here, okay, like the apparent atomic mass of hydrogen would then be 0.084 AMUs. And I guess I don't want to use grams here. We're going to use AMUs. And this is our new AMU scale. This would be for carbon and for hydrogen. And we can do the same thing for oxygen here. You could say, well, we have normally 12.00 AMUs. Oxygen is 15.999. And then this one would be okay, this one would be 1 divided by 12 times 15.999, or 1.333. So if we didn't know about hydrogen, we might say, hey, carbon's their base unit. I mean, this is kind of a silly problem. We're not going to be doing something along these lines, but I had this one in for my lecture notes, so I thought I'd throw it in there. I think the textbook has a couple problems where they have you like asks, hey, what if you were on Jupiter and you had a new atomic mass where this other element was the basis. In fact, like for a very long time, hydrogen was considered the simplest element, and then oxygen was, and now we use carbon. So things have changed a lot over the years, and hopefully this lecture helped you kind of have an understanding of the differences between matter and energy forces, and some of the things that led to the discovery of the atom, the different laws. And in the next lesson, we'll talk more about the history of the atom, and we'll talk about isotopes, and I think it will be a very useful lesson for you. All right, take care, everyone.